not to apply, and Internet 2 and the 39 state and regional networks that we collaborate with in the US put in a number of grant applications, and over $1.4 billion was allocated to network infrastructure. Internet 2 got $100 million of that. I mean, we built this new network that is the first dark fiber network that Internet 2 has owned. Previously, we were on a leased network. And obviously has a fairly robust footprint. For those of you that know our old maps, there are a number of extra lines on this one that weren't there on our old network. As we started this investment, it was clear we had to buy fiber, we had to do contracts for electronics and other such things. One of the things that we started asking ourselves, and our new CEO, who's sitting right there, was pounding on the table about this, is what are we going to do with this investment that's going to differentiate us? And create opportunities for universities that will make the Internet 2 different, the Internet 2 network different for a long time to come. Essentially, what's our innovation strategy? And what do we need to do to enable that network infrastructure, make our investments in a way that would set the users of the network, the university, researchers, and others out in front. We spent some time thinking about. Did I turn that off? No, someone else did. Okay. We spent some time thinking about the conditions that have enabled innovation in the past, and went through a process of thinking about those things that we thought in this current era could really enable great innovation for the future. And I think my slides are out of order here. Hang on a second. Okay. So you think about the past and the things that have happened in research and education communities, particularly in the early era of internet innovation, where we had people in our universities and our labs writing protocols, we had people writing applications on the fly to do neat new things like video, and we had companies coming out of our universities forming the major inflection points in information technology. And we thought about some things that are really critical there. One was abundant bandwidth. We had an opportunity to rebuild our network. We decided that we would go all 100 gig coherent, and that we'd change our pricing model to encourage adoption of 100 gig services on the network to enable folks to innovate on top of that, so that bandwidth would no longer be a constraint. In the 10 gig world, we were starting to see, particularly in our interconnections to the regional networks and their interconnections to the campuses, that folks were starting to game the system again. They were focused on what the financial inputs and outputs were to optimize their connections as opposed to encouraging utilization of the advanced networks. So we spent a lot of time talking about what we could do to change that. And in fact, we changed our fee model. We used to charge $550,000 for a 2 by 10 gig connection. We changed our fee model to be $200,000 for a 100 gig connection. And most people, of course, bought 2 of them, saved some money, and reinvested in their campus infrastructure as well to upgrade those connections. Regional networks in particular who connect to us, but also they carried that forward downstream towards their end users. One of the other things, ESNet had been doing a lot of work right around this era on science DMZ. And generically categorize this as really intentional about supporting large data flows at the security border of the campus and making sure that you have data transfer capabilities for very large flows. Again, to separate what we do in the RD community from what's happening in the commercial networks, where they tend to focus on millions and millions of very small flows stuffed into a pipe to the 90% maximum utilization. We instead said we want to go to 100 gig pipes, so there's an awful lot of room for bursting, and we want to make sure that we enable the applications so they can burst into that abundant bandwidth. So, following ESNet's lead here, we've been encouraging a lot of our campuses to adopt Science DMZ, have had some impact on other funding programs that have allowed campuses to really move on that. Also, we put a lot of effort into software-defined networking and thinking about, if you think about what's happened over the last 30 years since the basic protocols and the internet have evolved, that so many of those have become very close proprietary protocols. When we want a feature installed in one of our routers or switches in our networks, we make a feature request to a vendor who decides whether or not to put it into the roadmap, and may or may not, 6 or 9 months later, come up with something that we can use. The promise of SDN is that we can regain that control, and that the very unique, thousands of innovators who are in our community can once again try new things. Now, yes, they may need to start at some very basic, low low-level programming levels and build up libraries of useful things over time. But reopening innovation, making sure that we have access, direct access to the basic forwarding infrastructure as something that we offer on our network was something that we thought was very important. So we started a partnership with Stanford University in Indiana to look at what we could do here. And in fact, as we came out of the network build, our entire 100 gig national backbone is now exclusively open flow. On Brocade and Juniper switches, we do not use the CLI, and we do not use their operating systems on our national backbone. It's been in production for 2 years. We've had pretty good luck with it. The majority of our failures are hardware failures, or things we didn't think about in terms of failover methodologies, because we have to write the failover methodologies now. But in terms of the risk thought we were going into instantiating that for our production network, we've done much better than we thought it might go. It's been much more successful than we thought. We also spent some time thinking about campuses, and again, this program that we talked about where we encourage the campuses to do support for data-intensive science, open up the programming stack, and move to 100 gig. We initially had 3 campuses when we launched in 2012. And as of today, when we closed the pilot, we have 31 campuses and 9 regionals who have agreed to install all 3 of those components into the infrastructure from the campus all the way through to the Internet 2 backbone. So here's a map of kind of where they are. This map actually needs to get updated. The person who used to update this map is no longer with Internet 2. It hasn't been updated since April. We need to work on that. But it gives you an idea, and as you look over the chart on the side, which I guess you can't really see, Science DMZ and 100 gig connections are things that people have been really focusing on. SDN's lagging a little bit behind. We kind of knew that would happen. But there's still substantial SDN adoption happening on the campuses as well. 4 campuses, 3 regionals were originally there. 22 of the 31 pilot sites have now completed all 3. 22 of the 31 have now received federal grants from the National Science Foundation to work on this, and in fact, we've had very good success in aligning what we're doing with what the National Science Foundation is supporting. And of course, in addition to Science DMZ, Persona is a key component here, so you can actually look at the performance coming out of these networks that we built. In terms of what this meant on our backbone, this is our traffic graph, and it's interesting. So we started this program. Let me get a mouse over here and let's see if we can do this. Maybe we started this program, started making decisions about it in 2010. Really started implementing in 11 and 12, and we are seeing substantial growth on the backbone as a result. We have folks, a couple of the early adopters on California and on the East Coast at Clemson University, regularly pushing a 90 gig flow across the Southern Path on demand, which is great. That's what it's there for. Of course, for those of us that have to budget for this thing, we're a little worried about the curve of that graph, and if it's really going to go up that fast, or it's going to start to ramp down. But clearly we've had an impact on utilization as a result. So 2 years ago we were 26 petabytes a month. We're now at about 53 petabytes a month. And if you follow the line, it says that by the end of next year we should be at 80. I'm hoping for 60. It says 80. So we built all this infrastructure. And it's interesting to see what people start doing with it. And we've spent some time now thinking about, what's the next step for this program? There seems to be pretty good adoption. People are moving forward in terms of the way they're thinking about this. And so we've spent some time in the last year thinking about the key users of this network. In particular, the pilot campuses and the programs they're involved in, Exceed, which is a distributed high-performance compute project in the US, and various other things we've been hearing in terms of feature requests from the network. We've been trying to think about what the investment cycle from these federal grants going to the campuses means, and in particular the GENIE program, which is kind of our network research program in the US, and even programs like US Ignite, which is a kind of spin-off of GENIE that's focusing on municipal cities and towns doing applications development for everything from track the garbage truck and when it's going to come pick up my garbage to helping make sure the Meals on Wheels gets to folks in need in a timely way. So how do the innovative applications that are happening in our community and in affiliated communities come into play? Clearly, the other things happening in this period of time is the trends around big data moving to the cloud, high-performance computing, software-defined networking, are increasingly aligned. And when we look at the kinds of things that Exceed's doing, now they've been around for 10 years, but the kinds of things that they're asking for to deliver network applications, or I should say compute storage applications, well over the network, the kinds of things that are happening with Genie program and Ignite, there's a lot of alignment and overlap in what they're doing. There's just not much orchestration between them other than people like us running back and forth between meetings. And so, we're trying to think about how to bring that together. This year, the National Science Foundation had a solicitation for 2 large cloud programs, and we've been working closely with them. One of the ones that we've been working very closely with, the Open Cloud, is actually talking about building an orchestration layer that will integrate an SDN network with compute and storage. Giving you a provisioning dashboard that essentially allows you to do many of the things that one would imagine would be very hard today in a very simple way. I'll show you one picture of that. In terms of Exceed, a lot of their applications now are thinking about how they get from their primary sites out to the other universities that are using their resources. Indiana, Purdue, connected at 100 gig, National Supercomputing Center, and others are connected at 100 gig. And they're really starting to leverage this network for some things they're doing there. They haven't thought much about SDN yet, but we're starting to hear from them that they want to move to a much more dynamic provisioning model for delivering the content that gets created in Exceed. There's a project happening on the campuses called ACI Ref, which was formerly called the Condo of Condos. And essentially this is all these campuses have consolidated compute on HPC, small HPC clusters on the campus into their central data center. And now they want to figure out how they can do that across campuses as well. So they call it Condo of Condos. It's got interactions with things like the Exceed project, with other National Science Foundation, high-performance computing resources, but increasingly it's really interested also in talking to things like the Genie project and the innovations racks that Genie has deployed, or with some of the SDN activities that are happening on the campuses. So they've been asking us, how can the network help facilitate their activities? I did have one example that included our friends here in Sweden. This is a ICT Biomed project, an international consortium of biomedical computing. It's basically about a computational biology model. But it points out that what we're trying to do in the US around innovation platform needs to be extensible to our relationships with other emigrants around the world. And we need to figure out how we can deliver these advanced capabilities through the open exchanges and through the global network architecture to enable not just purely domestic examples like the other ones, but ones like this as well. The Genie project, many of you know, is a network project where the network researchers spend a lot of time developing various paradigms for advanced networking. In the last several years, they've shifted a lot of their attention to deploying these Genie racks. And there are, I believe now, more than 50 of these deployed. You can tell it's a pretty hefty amount of compute. It's got an open flow switch at the top, and they're plunked down around in the black dots around the national network. And people are trying to figure out what to use them for. And they were put out there for this purpose, to kind of enable folks to do applications and small HPC, distributed cloud kind of applications. The program, I think, is an interesting function point because now there's a big deployment and the applications are lagging a little bit behind. And so there's a lot of energy going in to figure out what to do with those next. So the Open Cloud example, here's a picture of the provisioning dashboard that we saw a couple months ago. This is a research cloud designed to support both cloud builders and cloud users. It's designed for cloud architects that want to experiment with kind of clean slate cloud designs and low-level cloud provisioning mechanisms. So the example that someone gave to me is, so let's say that you want to be able to take 5. Well, let's just say we know there are 10,000 cores across the network available. I'd like to grab 2,000 of them. I'd like to build a network between them. To create a private closed network between the compute capabilities. I'd like to expose it to the internet in a couple different places. I'd like to load some software on to all the VMs in that system. And I'd like to load a genomics data set. Instantiate. And essentially that's where he's really close to in this dashboard. And he's actually at a place where he can use the open flow paradigm to provision the network, use OpenStack to go and create the VMs within the compute infrastructure. And they're working on the orchestration of how you would load the applications and how you would do other kinds of things. We think this is really interesting for a lot of reasons. Mainly because once you get here, no one is going to want to talk to me about the network anymore. Because this kind of dashboard is going to subsume all the kinds of things that we've spent a lot of time talking about in developing language and service definitions with our end users about over the last couple of years. So this is the part where I transition from what we're observing to what we're trying to figure out. Clearly the network function virtualization, the move to virtualized machines, the move to the cloud, and SDN trends make us think that we clearly have to stop looking at the network as something that delivers service on its own. It's a subcomponent of the more important services that things like OpenCloud and NSF, the other two NSF cloud projects are trying to develop. I think someone said this morning, it's about the content fundamentally, and that's absolutely true. So how does our innovation platform strategy evolve to support that and continue to be a really robust infrastructure component, but be really open to those folks kind of just kicking it over and innovating on top of it, instead of thinking of it as they do today as a black box that they have to conform to and move bits through. So what are the abstraction layers we need? What are the orchestration layers? And what level of compute storage do we need, not only in these big clusters, but in the supporting infrastructure? How many VMs do we need distributed across the network to run the network function virtualization that folks need to run these private clouds? Are all questions that we're kind of grappling with today. I think the good news about this is we learn about all the things people want to do with this. We think the basic fundamentals of opening up the software stack of the network, allowing software-defined networking, thinking about abundant bandwidth and 100 gig, and being really intentional about supporting data-intensive science are still critical and still work 2 years later, but that we've got a lot of work to do to think about what comes next. I'm good. So, more thoughts on some of these, big data sets need to move pretty ubiquitously between compute research. I think someone this morning mentioned publication and archiving, also very big issues in our community, and there are a number of projects starting up to try and bring those back into the community as well, to kind of regain control over the way that we publish and archive various academic resources. We do see some commonality clearly in the basics of what folks want in compute storage across all the disciplines. That's probably not a surprise, but it's nice to know that it's true. And clearly the virtualization that's happening in compute storage enables that anyway. Trust and identity is a big issue here. And in fact, it's probably the first time in a number of years where our trust and identity effort and our networking effort are really critical to each other. We've also heard from our university something very interesting. We're still trying to figure out exactly what this means, that Amazon is great, but it's not deterministic enough. I can't move to the cloud. I'm not willing to give up my local data center to move to Amazon yet, because it's not predictable in terms of when it's going to get the job done or how I'm going to get the data in and out, etc. And that we as a community still need private resources. We just want them to be as close to Amazon as we can, but more deterministic than a pure move to the cloud. And finally, one of the other things we're hearing very clearly is that once these data sets and these clouds are created, they are not focused just on a domestic audience. They have to be available for access and use on a global basis. So, we're thinking about tighter integration of compute and storage, how that works in the Internet 2 environment. Most of these resources are going to be out on the campuses or potentially in the regional networks. Probably the highest cost colo and power environment in the US is RPOPs. So the more that this stuff gets pushed out to the edge, the better. Of course, that means that 100 gig to the edge and SDN capability on an end-to-end basis is really important. We're working with these 3 projects now, 2 that were funded and 1 that's working independently for these large-scale NSF cloud orchestration and service delivery models. And it looks like at least 2, maybe all 3, will begin to use an SDN OpenFlow substrate to underpin their cloud capabilities across the backbone in the next year or so. And we're thinking about whether or not there is some version of community environment that would be constructed that would have the ability to prototype what's possible in a very small scale environment so that we could then push it out to folks like Amazon, but to make sure that we have the leadership position to define what's possible in advanced infrastructure as a service. There's a big investment curve associated with that, and it's a topic that's getting a lot of attention in the US right now. So, again, abundant bandwidth support for data-intensive science, programmable and virtual networks is really important to match up against these new integrated virtualized cloud and compute storage that we're working on. And this question about on a global scale, does the innovation platform necessarily in this next era need to include some level of orchestration and virtualization capabilities in addition to just networks? That's it, until we get to questions later.
Thank you very much, Rob, for being well on time and an interesting presentation. We do have time for one or two questions.
Post-lunch phase.
Going once, going twice. I have a question for you, Rob. Yep, there we go. You talked about a number of challenges you see ahead for the network infrastructure. This is the innovation and networking part. You showed the exponential graph. You're expecting 80 petabytes per month. When you look at the traffic next year, you were hoping for 60. You talked about other challenges. What do you think are your biggest challenges going forward to make sure that in 5 years down the road, you still can offer your constituency a perfect network service?
Yeah, so the funding and the bandwidth scaling stuff are things I think that are pretty well understood, and that's just we understand that fight. I would say this, the complexity of operations related to the software-defined network and kind of bringing back in-house production-grade development and service delivery and trying to be innovative while running a production service is much harder now than it was a couple of years ago. So we're spending a lot more time doing lab work before we do a change. We're still, because we're taking a lot of responsibility for the programmability of the network back in-house, a lot of times we know more than the vendors do, and they're going much deeper into their support organizations to be able to support this network. So I think that's going to be the interesting curve probably for the next year or two is how much more effort we have to put into supporting it, because we were pretty darn good at running a basic IP forwarding play.
Okay, thank you, Rob. Lars?
So thanks a lot, Rob, for a very interesting presentation. So 2 years ago, we had Steve Wolf come and tell us about how you plan to do your entire backbone based on OpenFlow. And I was looking forward to the big crash report this time, and it didn't happen, so congratulations. You've been daring an innovative there. But it leads me to ask a question, something I'm grappling with, and I think a number of veterans are grappling with it. I'm seeing that more and more we are becoming software shops, and we are not, I think, as organizations geared toward that. We don't have very many software developers, and we're not used to hiring software developers, thinking about software developers. We still, we have a bunch of optical engineers, and we see that much of what we have to do is writing software. And so you must be further along that curve than we are. So I was wondering if you have some thoughts about that.
Yeah, I totally agree. So, the quality of the software engineering and the processes around deploying software are much more important than they were. We have very good partners in the way Internet 2 does in software development. A lot of the requirements gathering and thinking about what we want to do is Internet 2 staff in Indiana does a lot of development work. And they've been spectacular in this space. I would say it's not just the software challenge, but it's also for us thinking about how we get our team defining services and building service roadmaps and being much more deliberate about the effort that goes into software development, turning into things that end users actually want. So that we don't get on this path where we just have people building a career around a particular software product. but instead are thinking about building a career around delivering great services to end users. As engineers, which I clearly count myself among prior to this job, we love to build and improve our own stuff. And so we've got some challenges there too around making sure not only are we developing great software, but that we've got a path out of developing that software, that we're focused on the services and defining the software improvements based on the services folks are requesting of us. And that's a lot of work too, and it's different than we were doing when people were just talking to us about BGP sessions.
Okay, thank you very much, Rob. Okay, on to our second speaker for this afternoon. Our second speaker is Arne Østenbø, and he can correct my pronunciation of the Norwegian name as soon as he has the mic. Arne is a developer at Uninet, the Norwegian NREN. He has been working for Uninet since 2001, and he's active in network management, passive high-speed monitoring, and he has made great contributions to Stager, pronounce that correctly, Emperor Summer, and C. And since he's now set up, Arne, okay, the floor is yours.
Okay, thank you. So in this talk, I'm going to present using commodity hardware for large-scale passive monitoring at speeds up to 10 gigabits per second. So Uninet has a long history of running and using large-scale monitoring infrastructure. So we use this for both active and passive monitoring. So right now we have about 25 probes, we'll soon have 30. That's distributed all around our country at universities and university colleges. We also have 2 probes up at Spitsbergen, so it's probably the northernmost monitoring probe in the world. So, so we use this infrastructure for both active and passive monitoring. We have, for example, multicast beacon to monitor the quality of multicast. We also have a tool called QStream, a screenshot of that one, but that can connect to multicast channels. For example, we have multicast TV that we offer as a service and a network. So with QStream, we can connect to the TV channels and measure the quality. We have a simple ping service called nping that pings all the measuring probes, so we can measure packet loss and round trip times. We have a web interface on the monitoring probes called npweb, where I can also do throughput tests. We have actually 2 different throughput tests. One that's relatively simple, using JavaScript. So there you can use cell phones, iPads, and so on, so to get at least a general idea of what the performance is from your device and to the monitoring probe. But we also have more advanced testing using iPerf. So you can do iPerf test from the monitoring probe and to your client if you start the iPerf server running on that one. And we also use it for passive monitoring. Right now, the main application is AppFlow, which uses deep packet inspection to categorize network traffic based on the application that generates the traffic. And we're also starting to look at intrusion detection system. There we're using Suricata. So in this presentation, I'm going to focus on the passive monitoring applications and also the hardware being used. So I will talk more closely about detail about AppFlow and Suricata later in the presentation. So this is the hardware setup that we have for the monitoring probe. As I said, we've been doing this for almost 10 years. So in the first generation, we had GPS antennas, but we have seen that really causes more problems than it's worth. Usually the servers are installed in the basement, as in the IT department and IT rooms, while the GPS antennas is up on top of the roof. So it means that it's long cable runs. And we also have a tendency that every time there's a big thunderstorm, at least one GPS antenna stops working. And we also saw that for real practical measurements, it wasn't that important to have such an accurate timestamps. So the good NTP server is good enough. But we had used it for some research projects where we had PhD students and master thesis working on it. But in the newest generation, they just stopped using it altogether, since it saves a lot of work. The measuring probe itself is just a standard server on one U-box. You then have a passive monitoring card. Earlier, we used specialized hardware for that card, also for their cards from NDAs, and also we had some cards from a company called Napatech. But in the newest generation, we just use standard commodity hardware, so we just use a standard network, or a high-end network interface card. The passive monitoring card is then connected into using an optical splitter between the unit router and the internal router for the campus. The optical splitter usually 80-20, so it means that 20% of the light signal is sent to the monitoring card. So just use a completely passive, looking at all the packets that goes on the link. The current server hardware, we use it as a standard Dell server. It has a quite fast CPU, 2.9 GHz. It has 8 cores and also supports hyperthreading, which means that the Linux, which is as we use to run Debian on this server, so it sees this as a 16 cores CPU. But the server also has support for second CPU. So on the measurement probes that are seeing the most traffic, we probably have to upgrade this second CPU soon to be able to handle all the packets. We are running 32 gigs of memory, but again, on the most, the biggest measurement probes, we probably have the most traffic. We probably have to upgrade this when we start running Suricata and doing intrusion detection. The card that we're using for passive monitoring is an Intel X520 DP card, which means that it has 2 ports with pluggable SFPs in it. So you can see that this is the card we use for passive monitoring. So it only has the cable that comes from the optical splitter is then split in 2, and it's connected into the receive port on both cards. So it's just completely passive, so no signals are sent out at all. The reason why the Intel X520 family of network interface cards is so good is that it has quite a lot of hardware support that can be used for passive monitoring. Originally, the card was designed for virtualization, also for servers running VMware and things like that. But those hardware mechanisms can also be used for passive monitoring. One of them is support for multi-core processors. So that's built-in hardware support for load balancing. So it looks at, so it generates a hash based on the source destination IP address and source destination port number, so that all packets belonging to the same flow is sent to the same queue. So that you can have one thread processing all the packets for that flow. It also supports DMA transfer of captured packets, so the main CPU doesn't have to be involved in capturing the packets, so you save quite a lot of CPU cycles on it. But if the memory or the PCI bus or something like this is full or is saturated, the card might have to drop packets because it can't send it into the memory. And then it contains hardware counters that tells you how many packets it has dropped. So that if you do quality of service monitoring and you detect packet drops, you can actually find out if it's packets were dropped on the card or in your monitoring probe, or if they were actually dropped on the network. And it also supports both 1 and 10 gigabit per second by just changing the SFPs, which was quite convenient for us since most of our customers have 10 gig, but we still have a few that runs 1 gigabits per second. So it means that we can use the same hardware for all the customers. But even if the card is really good for passive monitoring, the standard drivers is not the best option. So it's better to use specialized drivers that are designed for passive monitoring. As if you use a standard driver, it can be good for up to a couple of gigabits, but if you are more than that, you will use like too many interrupts per second. So there are several options if you want to use a specialized driver. When we started this project last year, we tried out 3 of them. We first looked at something called Packet I/O Engine. It actually was quite easy to install, and we really liked it, but it had a few bugs. And when we tested it last year, it looked like it was no longer maintained, because there had been no activity on the repository for more than a year. But I just checked last week when I prepared this presentation, and actually have been a few new commits right now, so it might be worth looking at again to see if they fixed a few bugs we had. We also have something called NetMap. It looks really good, but it's a research project for the university in Italy. It was originally developed for FreeBSD, but the port that they have used to Linux is not stable at all. Again, there's a new version available, but I still don't think it's production ready. So what we ended up using is something called PFRig with DNA drivers. So this is developed by Luca Neri, that's also behind the NTOP tool, some of you might know. So this is very stable and well-maintained code. It also has the added feature of allowing multiple applications can access the same buffer at the same time, so you can run multiple applications doing a passive monitoring. Some of the code is DPL, but not everything. So especially the DNA drivers that you need to get high performance. But they are free for academic use, otherwise you have to pay a license per interface. Here you can see a little bit about performance. We tested this in the lab using a packet generator. So first we tested with just minimum packet size, 64 bytes packet size, using both ports on the card at the same time. And we used one single core for each port. And as you can see, we managed to get up to about 25 million packets per second with no packet drop. But then we were using 23% of the CPU just to capture the packet and do nothing else. If we went full speed, that's as much as 29.8 million packets per second, and we had lost just over 3% of the packets. But if you start using a little bit more realistic packet size distribution, and then we also used 8 cores for each port, so we can distribute the load a little bit more, and then we managed a full 20 gig per second, also 10 gig in each direction, and that was about 6.5 million packets per second. And then we had 0 packet drop, and we also used just 9% of the CPU load to capture the packets. So based on these results, so if you really want to capture every single packet, even with minimum packet size, then you really need to use a specialized hardware, like the DAC cards from Mendes. But if you want to do more realistic measurements on realistic traffic, the Intel cards are more than good enough and can manage the full load of normal traffic. But when you're deploying infrastructure like that, there are some things that can go wrong. And from the 10 years that we've been doing it, we have more or less seen that everything can go wrong. I already mentioned the DPS antenna, so that's probably what causes the most problems. So I said that we don't use that anymore. You also see we had a problem with servers. They haven't survived shipping, so even if you have set it up in our offices, we just send them to customers. It hasn't worked when I turn it on. So that hasn't happened with the newest generation, but the previous one actually happened twice, I think. We also had some problems with the passive monitoring cards, but again, that was the previous versions. So right now, the main problem we have is with the optical splitters. What we're seeing is that as while the splitters are configured so that you can, if you have a direct connection between our two routers, you can just take the cable, plug it into the splitter, add a second cable down here, and a third one that goes up to the passive monitoring card. But what we've seen is that in some installations there are some patching panels involved, and they sometimes cross the cables. So what happens is that when I connect it, the input signal actually goes into the 80% out of the splitter. You still get a connection between two routers when you do that, but you don't get anything at all to the monitoring card. So the problem is that sometimes only one of these have been split. So it really depends on how things are set up. Sometimes both of them has to be fixed, and sometimes just one of them. So we have written quite detailed documentation with pictures, but they still have to go out and help people connect these splitters. So that's the main challenge. Otherwise, I would just say so it really helps also to use standardized hardware. As I said, even if we don't need a 10 gig card on all the customers, we still have shipped that out so that everything is similar on each and every installation. So a little bit more detail about AppFlow, as one of the main applications that we use for passive monitoring. As I said, NetFlow uses deep packet inspection to categorize network traffic. So you can see what kind of traffic is HTTP traffic, as regardless of the port number. You can see BitTorrent traffic, Skype traffic, and so on. So the main tool is NProbe, that's also developed by Luca Levi. So that's actually what does the classification of the traffic. But in that sense, then out IPFix flow records that contains extract attributes that defines the application that generated the traffic. But what we saw is that if we, as a traditional setup, where you have the probes that just sends out directly the IPFix information to collectors, and this actually generates quite a lot of traffic. Just one, the most monitoring probe has the most traffic. That's about up to 6 gigs back and forth in peak traffic. That can generate more net flow than all the core routers that we collect sample net flow for. So it means that with 30 probes, we would have to have a lot of collectors if we wanted to collect all the flows and the processes afterwards. So what we did instead is to create a small aggregator that runs inside the probes. So this one in real time collects the flow records and generates aggregated statistics. So we ship out every 5 minutes. So that's a lot easier to handle with the collectors, because then we just get reports every 5 minutes instead of the thousands of flows every second. NProbe also has support for geolocation, so you can also tag the flows from which country they come from, and also the AS numbers. We also added a short script that can take our prefix database, so that instead of just getting that the traffic goes from Uninet to Uninet, you can actually get that it goes from this college, the university college, to this university, and so on. So you get more detailed information about where the traffic comes from. We also generate aggregated flows for, as we generate the total traffic. We have the most common applications used, both for IPv6 and IPv4. And also for each application, we look at which countries they come from and which AS number they goes to. Here you can see the web interface for NFlow. So you have the applications on this one. Also the number of unknown traffic varies quite a lot from the different monitoring probes. It can be as low as 20% on some of them, but also as high as 60–70%. So that's something we're looking into to try and get that as low as possible. So when you select an application, you can then see on the map where the traffic comes from and goes to. And if you move the mouse pointer over, you will get this information about exactly how many percent that went to that country. You can also get more detailed information about IPv6 and IPv4 and how it's running. Right now it shows just the daily traffic, but you can also get weekly, monthly, and yearly. And you can also get the information about the AS numbers, so where the traffic comes from and goes to in more detail. When it comes to performance, it's actually quite good. It is better than we expected. So you can see here, it's a monitoring probe that has, this is both links of both incoming and outgoing traffic. But you have a peak of almost 5 gigabits per second, or 800,000 packets per second that was processed. And you still just use just over 10% of the total CPU power to process this. So that means that we have even on the server that has the most load, and so we can also put in a second CPU. We have a lot more CPU cycles to use. That's why we started looking at intrusion detection as well. So this is just so far in the test phase, but we are hoping to get it up and running later this year. So Suricata is a rule-based intrusion detection system. It's compatible with stored rules. So here's just a short example of a rule. We're going to look at HTTP traffic, regardless of any IP address or any port number. So it means that it can recognize HTTP traffic. So this example is just taken from a tutorial that's online for writing rules. So it just says that you want to search HTTP traffic for the word Scarlet. And if you do, you get a message that says, do not read gossip during work, and it's classified as a policy violation. But you can have quite advanced rules for the Suricata. It also supports decoding of quite a lot of layer 7 protocols, so you can decode and specify filters for all the headers of these protocols. It also has an advanced HTTP engine, so you can get full request logger for HTTP request. And you can also log, and even, if you want, you can even store files transferred with HTTP protocol. So some people are using that to do automatic virus scanning of files downloaded from the network. And it also has DNS logger, so you can log all the DNS requests and answers. There are quite a lot of rule sets available for Suricata. We use something called emerging threads. So far, we're focusing on ET Open, as emerging thread open. That's freely available. It has more than 15,000 rules. There's also a professional version available that has around 19,000 rules. That professional version is updated daily. The open version is also updated quite often, but very often it lags behind, a couple of days behind the professional version. But the main difference between the open and the professional version is that the professional version contains a lot more rules for malware detection. It requires a lot of research and advanced rewriting to be able to work on it. So if you want to use professional version, you have to pay a license per sensor. I'm not going into details with it, but this just shows an example of what kind of logging information you can get from Suricata. So here you can see both the alerts for intrusion detection. The first part is common for all logging types, and then you have the specific ones. So you have for alert, you have for HTTP, that shows the URL, the host name, and also the user agent, and you have the DNS, where you can get full information about DNS requests and answers. But it can be quite a lot of logging. So even on a medium-sized probe that we've been running this on, we got as much as 1.7 million entries in just 1 hour. That was during a relatively low attack, DNS reply attack for it. But it means that you have to have quite a good backend to handle all the logs, especially if you want to scale it up to 30 monitoring probes. So we are using Elasticsearch, Kibana, and web interface. There's actually going to be a presentation of, no, sorry, that's not this time. But Unit is putting this up as a service for customers where you can get Elasticsearch and Kibana up and running for all types of logs. And alerts from Suricata will then be one of them. So Kibana is the web interface for Elasticsearch. For those of you who are familiar with Splunk, as Elasticsearch, Kibana, and Logstash is the open source alternative to Splunk. But it gives you very good performance, so it's fully scalable, and you can really dig into the data and find out what's happening. So it's just an example of the web interface, where you can see the number of log entries over time. You can see alerts, so the alerts are divided into different severity levels. So you have severity 2, the small one is the most severity 1, and then you have 3. And you can also see that which countries most of the logging comes from. You can see China is quite high. And then you can also see different alert types, and then you can click on this and really dig deep and find out what's going on. And then this last slide, the current status. Right now we have 25 probes up and running. 4 more are used for active monitoring, but the splitter has not been installed yet. 2 of them have problems, they've tried to install it, but it doesn't work. So then we have to help them. And 2 more is just wait, as they haven't bothered installing it yet, because they're still going to upgrade our network. So instead of breaking the link right now, they just wait till the new installation comes up. And we have one that's been shipped out, that's to Spitsbergen, so the northernmost, so that's waiting for installation and should be up and running very soon. We have the active services, and then I already mentioned that for ping and so on. Suricata and IDS, that will come up probably hopefully in a month or so. But after Suricata, we're also looking at what else we can do with this infrastructure, and what we hope to start looking at next year is distributed IDS. Start looking at data from all the probes. If we can start correlating data, we are hoping to be able to detect all the things that not some single probe can do. And also, again, using both data from the IDS system and also from AppFlow, we might also be able to do more advanced anomaly detection. For example, if unknown traffic starts increasing on all probes, something might be going on. Or if one application becomes suddenly a lot more popular, you can start looking at it. But again, it's correlation of data, so we hope to get next week. Okay.
Many thanks, Arne. We do have time for 1 or 2 questions. I see one over there. And then Lars.
I can also solve it because I wrote down the questions. I'm just curious because when you have this new fancy processor offloading network cards, are you able to record all the packets, even bad packets, or will they be discarded by the network cards?
Bad packets will be discarded, so if yeah.
Okay.
Yeah.
Pretty much you already answered my question number 2, which was about the scaling, but what are the limiting factors of it? I mean, if you, for instance, wanted to put another 10 gig cards, is it CPU or the PCI bus, or what's the limiting factor?
As if you want to have 2 10 gig cards in it, then the limiting factor will be the PCI bus.
Okay.
Yeah. But the CPU can also be a limiting factor depending on what you want to do with the processing.
Which really boils down to the fact that 40 gig and 100 gig is pretty much impossible today, I guess.
Well, not if you have the newest generation of PCI bus. There is a Czech company called Invertech. They just released a 100 gig monitoring card.
So everything will be better in the future.
Yeah.
Okay, thank you. Lars, coming your way.
I was just wondering, all this impressive stuff you're collecting and the IDS stuff and everything, I start worrying about privacy.
Yeah.
You've had any considerations?
Yeah, I can yeah, 2 things. So I forgot to mention that one about AppFlow. One advantage of doing the aggregation inside the monitoring probe is that we throw away the IP addresses as soon as they've been counted. So we don't export any IP addresses at all when it comes to AppFlow. When it comes to the suricata, then of course you only log something that's bad to happen. So these are alerts that something is happening. But of course, suricata can produce quite sensitive information, yes. So we have strict policy about who can access it and things like that.
Time for 1 more question. Yep, Jerry.
Just a quick observation or question. So if somebody is sending flows that are encrypted, then all this is invisible, right?
Yes. In AppFlow we also have behavioral analysis that works on encrypted BitTorrent. So you can actually detect encrypted BitTorrent based on how they behave. But of course that's always a race between so it changes over time.
Okay, great. That means we're coming to the end of your presentation, Arne. Thank you. And that means that we have 1 more speaker to go. Next speaker, last speaker in this time slot is Lars Fischer, the CTO of Norgenet. Lars has been with Norgenet for 10 years. And before he embarked on Norgenet, he was working for Tele2 and for Colt Telecom as a director of network services. And even before that, he was in research at, I think, Aalborg University, right? Yep. And I'm sure I don't pronounce that correctly. Lars is the last speaker in this time slot, and Lars' presentation is about deploying standards-based, multi-domain, bandwidth-on-demand services, and all the experiences that Lars has gained here. Lars, the floor is yours.
Thank you. So I was hoping there was an award for the talk with the longest title that I was going for that one. I don't know if I won anything, but there we go. So this is going to be about bandwidth and demand, and I'm going to try to relate to your experiences, stuff we learned, and also where we are with actually deploying bandwidth and demand, and not just making it a project for something we're toying around and programming for people who think that is cool. So just to get us started on where we are with that, bandwidth and demand started, I think, at least for the research network, back in around 2000, when we started doing hybrid networking. That was when many European research networks at least started having the opportunity to get their own dark fiber, and not just dark fiber, but got the experience to not just deploy Ethernet on it, but actual optical transmission platforms, doing SDN, which we sort of was great technology back then. Xi'an, in the Xi'an 2 incarnation, went for an optical platform. We gave the options of providing private circuits and private networks for block science users. The first early adopter of that was the LHC community. It was ordered a thing called the LHC Optical Private Network, but to interconnect all the tier 1 sites for that, to do the video distribution. That was back in 2005. It's been a long time we've been doing this stuff. And even back then, lots of people were saying that, but that's circuits. Come on, hang on. And some of us are, I'm one of them, old enough to remember when we were doing packets and people were saying, we talked about saying, packets will never work. Everybody knows that circuits is the way to go. You should take the 625 thing we have, will solve all the problems. So going back and trying to solve the research networking community circuits has somehow been a challenge, and there are people in our community who have never gotten past that bullet. Yeah, I'm sorry. I'm going to continue a little bit late, more of this, but it is a challenge still for some people to deal with it. Quickly became a realization that if we were going to have lots of science users adopting circuit-oriented networking, doing it manually every time wasn't going to fly. So the Glyph community also started to experiment with automatization, automatic provisioning systems, automatic control planes for this stuff, starting around 2007. There's lots of experiments, demos, people throwing stuff, mostly single domain stuff. There were some systems produced called Autobahn here in Europe, Oscars in the States, OpenDRAC, the Dutch did that, and with Siena, good result with that. And the Glyph community set up something called the automatic goal to experiment with that in a test bed that was distributed and had multiple domains. So multi-domain interoperability started happening. There was a DICE collaboration between Internet 2 and SNet in the US and a couple of European partners, notably Xi'an, that came up with some first tries at having interoperable automatic provisioning systems. So there was some advances in that. So we ended up with a scenario looking something like this. I lost my pointer. Sorry about that. Oops. No. Solo to the highest bidder. Sorry about that. Anyway, so we ended up with something like this picture with insights connected to NRENs, some open exchange point and large circuits in between, and control planes talking to all of these, possibly different control planes using different technologies, network in between using different technologies, but with the capability of setting up circuits between two endpoints and being able to fulfill zero-loss flows. So that looked like a possible scenario for people starting, thinking more about how are we going to make this interoperable. Obviously, we need to standardize, so they came about the NSI standard suites, which is really just a framework for doing network services. Primary of that is the NSI connection service standards that allows you to set up dynamic circuits, the bandwidth guarantees if you want it. You can use it for traffic engineering, directed flows, and so on. I'm not going into a lot of that, but there's a lot of people here who are doing NSI, some of them devoting their lives to it. We're grateful for it. I don't have time for that, but there was a full meeting on Monday. Some people can argue a lot about little details of that. That's a lot of fun, but we're trying to get to deployment of this stuff, so let's just carry on with this. So this allows multi-domain circuit routing and allows multiple implementations of the same standard, allowing different people to have different systems so they can all participate in automatic circuits. But somehow we've had this trouble. We've been doing a demo, and then we come back and we did the standard just a little bit better, and then we've done another demo, and another optimized standard, and more demos, and we sort of haven't never gotten beyond that. Well, we wanted to get beyond the endless demo cycle, and it's sort of a chicken and egg situation right here, because we have had a lot of real users using this stuff because there haven't been any really comprehensive facilities. The only facilities are demo facilities that are limited in bandwidth or limited in reach. So the astronomers or the HIP community or whatever they are haven't been able to really use this stuff, because if they want to do a 10 gig flow, no, you can't do that because it's just a test bed. Or can we use it to this facility somewhere in northern Sweden? No, you can't do that because we don't have that reach because it's just a test bed, and that's been a little difficult. And we haven't had really the deployment because, there hasn't been a user request because the user couldn't really use it, and there hasn't been enough deployment because even though they had a lot of stuff in the Netherlands, they didn't have anybody to peer with, so how was this going to work for inter-domain and international stuff? And there hasn't really been a usable inter-domain circuit service, so we decided, let's do something about that. And we needed to recognize it's no longer a technology problem. It's really, all the bits are there, we know how to do it, even though we can haggle about the standard, we really know how to do this stuff. It's really just a matter of sitting down, a couple of networks together, deciding to do it, and then just do it. So we decided to act, and we here being Thursnet, Norginet, and as we went along, the party grew a little bit, and Xian, the Danish research network, Dike, Foodnet, the Finnish network, and a couple of other people joined. And we like parties that grow, so that's fine. So we set up a small team, core team of Thursnet and Norginet people. We decided to have joint project plans, to disregard the fact that we're separate organizations, to have joint timelines and specifications, and to be open to input for the community, try to be very agile, having quick iterations, lots of deadlines, lots of early demos, but still be this core group taking input, because we didn't want to be distracted from the objective of getting to a result very, very quickly and be agile, and we didn't want it to turn into yet another committee and yet another standards body having a lot of talking. So there hasn't been a lot of talk with this committee. The mailing list has stayed mostly silent, but the results have been appearing. I like it when the programming to mail ratio is above 1. So we also decided to announce our intentions very early in the community, so to let other people who are working about the demand knowing that we have decided to stop doing demos and go to production. We made an announcement for the LHC community. I think I held the first one in December. Last year. It feels like much longer than that, but it hasn't really been longer than that, and we feel that a lot has happened since then. So the objectives of this community really want to facilitate real users and real applications of this. Right? It's not, it's not about enabling the initial users. We want to be doing this, and we want to not just do it alone, like lots of other projects have done. We've been developing provisioning systems, alone, but building a multi-domain provisioning system alone is kind of pointless. So we did this joint effort. We really wanted to get to an integrated bandwidth-on-demand service connecting all of Europe. Wanted to be multi-domain, as I said, multi-provider, and multi-technology, because some of the networks in Europe, like Norginet, have an MPLS fabric and provision circuits across MPLS. Others have an OGN fabric or a carrier-grade Ethernet fabric or whatever it is, and we have to be able to set up circuits end-to-end that use multiple technologies along the path. And absolutely have to be standard-based, and the only game in town for circuit provisioning standard is the NSI standard framework. There is nothing else to do. So we wanted to do that, and we're very committed to the standard process, but we want to advance it, we want to make sure things happen, and we're not caught up in endless discussions about it. So we're willing to make some choices and go ahead and implement stuff. So there's been a very close collaboration and advancing some things that were in the standard, AI and security, very important. Topology distribution, pathfinding has ratified the standards. We decided we wanted to work on policies and how to have link policies, how to manage the different links and different openings, things like that. These are things that are not covered in the NSI Connection Service 2 specification, and we wanted to advance those and do implementations that we can deploy in our operational networks and actually have it work for our users. And we wanted to get to usable not necessarily as perfection. We do know that some of the choices we've made alone, haven't discussed with other people, the standard bodies. We may have to go back and revisit those, and we may have to learn some things that may need us to go back and say, all right, we did the wrong choice, but at least we've gotten somewhere. So we went for usable and not for perfection. So we, for filling in the gaps, primary to that, I think, really was authorization. We decided authorization happens at the endpoints, usually using tokens, sometimes user attributes, but most of it are user tokens. So there's no provisioning happens, and we have deployed without authenticated access at the endpoints, which also means that we don't generally use authentication for the transfer links, which means that get to usable, not to perfection, we aren't at the point where we can administer link policies. We can't select between several links to go several paths to go to the same place based on this link allows high-energy physics, this other link allows only bio researchers or medical researchers because they're that group of people paid for the link. We don't have that yet because we don't use that for authorization. We use the endpoints exclusively for that. But we chose that because it satisfies most of our initial use cases. So we know there are things we need to return to, but it gets too useful. And we decided for pathfinding and for assuring topology that really it is a peering infrastructure, much like we used to do in networking. It's just data plane and control plane connectivity that constitutes a peering. The control plane happens over TLS, and so we're trying to do security here. And also, we had to think about how to do trust. And again, there are lots of options. You can decide that I don't trust anybody. If I want to provision things across circuits or resources that I own, I want to authenticate every single user in accessing those resources. We decided that for our collaboration, for our purposes, since we are research networks and things that are close group, it's sufficient to say that the endpoints authenticate, and if one of our peers, Surf and Xian, has authenticated a user, that user is authenticated to use the resources. That might not be true always, it might not be true going forward, it may not solve all the use cases, but for now, it's okay. So again, get to usable, not to perfection. I want to briefly stop here and talk about this. Renee had this up at the open plenary. Apart from trying to serve a couple of small use cases, a couple of research groups that want to do a circuit for their radio telescope or for their biomedical database access or for their particle accelerator, we're also working towards a space, as Renee mentioned this morning, where intercontinental networking is more and more moving from a space of I have my links to the States, Rob has his links to internet, 2 links to the States, Sean has their links to the States, to a situation where we are jointly buying these huge links and building huge infrastructures that we operate collaboratively and use together. And if we want to do that, we have to find a way where we can dynamically manage the resources and those links so that we can share them in between us. And this sharing of these joint resources is clearly a big problem that we are moving towards, and we have to find ways of doing that. So apart from all the other stuff we do about the demand of facilitating research activities, it's also about finding ways of managing these types of resources and building the technologies that allows us to do the sharing of these big joint infrastructures. That is tremendously important for us going forward. So we're working towards some specific use cases, but we're also thinking about this long-term view of managing resources for the global inference. So this is very important for thinking about the 2 things we're doing and the decisions we're making with what we're implementing. So, what have we done? We have a deployment now on our production platforms. We have working NSI 2.0 connection service implementations. We have several. FirstNet has one, Xian has one, Nugent has one. We have different software, different technologies we're using, but they interoperate. It's not another demo. It's on the production platform. And the important thing about that is it means it has access to the full capacity of our networks. So since it writes on our 100 gig links, if a user wants to allocate the bandwidth on demand 10 gig links, 20 gig links, they're there. We can do that, right? And we do have initial users of this. It's well tested. We have SurfNet, NordGNet, and Channel already connected on this. We are constantly adding connections, so there's new open exchanges coming in. There was just one at the University of Amsterdam, ThunNet, finished with SurfNet is connected behind NordGNet. We did a demo at the Trina conference in Dublin earlier this year. And essentially, since Xi'an is joining this, we are connecting most of Europe behind this as we said in one project. And we are collaborating with Autogol, so we have a even further outreach with that. So, just very briefly again, this is the graph done by Hans Trampert of SurfNet. It shows the combined infrastructures of what we have deployed and the Glyph Autogol. The green stuff up there is a control plane between NordGNet, SurfNet, and Xi'an. The blue stuff is the control plane of the Autogol, the Glyph infrastructures. That is more of a test bed, but is now declared to be a production thing. And then all the red lanes are the data planes, so those are where the two different types of control planes can manage and provision links. That covers, as you can see, much of the Americas, much of Europe, and a good part of Asia. So there really is a wide range of connections with that, and we can provision circuits that hits lots of different types of use of facilities and lots of networks. I think we've come a long way with this. I'll talk a little bit about what the advances we think we've done in the past 10 months we worked on this project. I believe we have at least made great strides to solving the authorization problem for NSI. We have something working that's deployed. We have solved multi-domain topology and pathfinding and topology exchange. We're using chaining, it works, it's the great stuff. Some people don't agree to that model, but you know, it's something we're used to in the Nordics. We know how to solve problems other people are slow to catch up. We have filled in some major gaps in the standards work and in the implementation work. I feel we've come a long way in just 10 months. It feels like more. And we have done stuff that is essential for having a production service, not just a demo. I'm personally surprised. This was one of the things I was thinking when we started that it's going to take a long time to get to any kind of consensus about how to do authorization, but you know, people were listening and the standards group seems to be adopting much of what we've been proposing, and this is going well. Pathfinding is a little more difficult. There's a lot of people who feel that we really must support the tree view of pathfinding and not the chain view, and either will. It cuts out. I'm back. Okay. So either we'll have to convince somebody, or they will have to convince us. There's some discussion in the NSI standards committees, and well, that's great. Disagreement is what makes the world move forward. So we've done some advances. We have stuff to do still. I think one of the most important learnings for me working with this is that before doing this initiative and trying to get to production, I have been spending with the LAC community, with the astronomers, with other users, lots of time thinking about, talking about what is the end-to-end service that users are requesting from bandwidth on demand. What is the service offering? And it turns out there's a range of options. Some people just want to manually provision stuff. Some people want a web page where they can go in and say, I want a link between these two sites now. Some people can say, I want to be able to schedule a series of links at different times. Some people want to have their application, when it has a data to transfer, to go out and request the link, set it up, send the data, and tear down the link automatically. There's all kinds of options for doing that, and there has, between user groups, user communities, end users, in sites, campuses, networking people, there's been no consensus and no really good understanding about what is the service, what is the service model, and what's the business model for these kind of things. And I've come to realize I don't understand this. I don't know what it is, because I haven't been in a position where I have anything to deploy and anything to show to users. I've never had a user in this, so how am I ever to be able to understand what the service is when I have no users? I need users to go and experiment with this. I need the physicists to go and try this stuff. I need the astronomers, the biologists to go and try this stuff, and then they have to come back and tell me, this worked for us, this didn't work for us. And so what I need to make sure as a network provider is that I have a capability, a circuit capability in my network that enable end users, user communities, research projects, local entrants, campuses to experiment with this stuff, to try different scenarios, to try different models, to evolve this service. And what we have been, I think, what, at least from my point of view, what I have been doing wrong is that I have been waiting to deploy something until I understood what the service was, which meant I never get to deploy anything because I never get to understanding what the service was because nobody had a chance to try anything. We are now changing gears and just deploying the capability, allowing people to do it, and then hopefully over a couple of years of experimentation we'll figure out what the service is. So that for me has been a major learning. Again, it's not about technology, it's just about doing it and realizing this is what we need to do. Right? So this for me has been important. And what we've done in Ordina, we have a provisioning platform. We're using a network control plane for our MPLS backbone system company called TLS. It controls all our Juniper routers, it speaks netconf towards them, it works great, we do it from drone peering fabric, everything is rosy, except there was this company called Cisco that just came and bought this TLS company, which is a Swedish company, and we're using only Juniper routers, and now we're not quite sure TLS is going to continue to support Juniper routers because maybe they have somebody who tells them that some other routers are more important, and I'm not sure where that's going, so we might have to be looking for something else. But now we know what kind of system that is. Maybe Henrik will have a job to write something that can do all this stuff, right? Not a big problem. For the NSI implementation, we have our own software, mainly done by Henrik, if it's right here. It has the complete implementation, does everything right. So that's not much to say about that. We're not the only people using it. It's all open source. It's deployed by people in South America, wherever. Feel free to try it out. Talk to us. And then for transport, as I said, we're using MPLS. Everything is MPLS tunnels. MPLS is available on our edges for the POD stuff. We deployed initially in London, Amsterdam, to big European exchange point, in Helsinki and Copenhagen, because that's where two early adopter end-runs are. But eventually we'll be everywhere. Norwegian has an MPLS fabric, which is our global network. And then we use control point security with TLS. Right? So the way it looks, we have this MPLS fabric that is everywhere that Norwegian has a network with some end devices. Faces either exchange points or partner networks. We have this NCS software, which is just a commercial software that is a console plane that we can use for any configuration of any router, including setting up MPLS stuff. It talks netconf to all this. And then we have hidden our NSI implementation behind that, so we don't have this homegrown software speaking to all our routers and making all our IP engineers very worried about us crashing everything. It just talks to the control plane software using HTML and XML. And then we have a network inventory system keeping track of all the resources. It's also a homegrown system that we can then use to keep all these things in sync. So we like the implementation we have. It works for now. It's good for us. Right. So we have. You probably can't see this, it's a simple web page we have where our NOC or whoever can go in and see which links we have, what is up and what isn't, and you can go in and click each link, and you can see lots of details about it, and you can, among other things, learn that XML has this nice habit of having impossibly long identifiers, and there's some people here are trying to read all the identifiers, and I'll quickly move on before they learn what's going on. We have an early user for this. Some early users, but here's one early user. It's a bioscience project based partly in Finland, partly in the Netherlands. So they need to set up circuits or to do transport between various places in Europe, and some of those core sites are in Finland and in Netherlands. And they're using dynamic circuits across FUNET, across NordGNet, across SurfNet to get to where they need to be going. And if you look closely at this, there's a couple of red sections, and that's because there are sections where we weren't, when they were doing that setup, we weren't quite deployed yet and weren't quite ready, so a few links were statically provisioned, but most of it is dynamic. You can also see there's some stuff where we hit the side, there's a shared open. That's because that's in London, and they have also a site for that project on Janet in the UK, and we can provision all the way to London, but the service isn't available on Janet yet, so we have to convince them to also deploy some of the stuff, so we can also provision dynamic circuits into their site in the UK. So, I'm quite happy. We're getting to production. In about 10 months, done most of what we promised ourselves we would do, and we are getting there. Of course, there's always more work. I talked about link policy, being able to choose between links based on owners or policies and those links is the problem we need to be solving and need to be doing something about, and I'm very happy. I noted it was on the NSI working group agenda this Monday, and I'm sure they've solved all the problems now, so we can just start implementing. Couldn't take that long. We still have to do a little bit more about the AI and the topology standardization, mostly on the topology side, because people aren't. We solved the problem. Why don't people understand? So Arne talked to us about monitoring for IP networks. We need to deploy good monitoring solutions for this. There's Persona that we've been doing together. We need to make sure Persona can monitor all this kind of stuff. Jerry has been talking a lot about performance verification, which is a comprehensive way of doing that. I'm sure he has another presentation on it, and someday we'll get to deploying some of this stuff. We have some work to do at home, some homework to do about finalizing our operation deployment to get to all our sites, and I have some operation managers and not people who come to talk to me about audits and security review and other nasty words I don't want to hear, but I probably have to hear them and do something about them. And we have to make sure we do really high quality tools for our NOC and our support people, because otherwise this won't fly in the long run. But despite having stuff to do still, the key message here is that we are really committed to maintaining an NFI production capability in our network and to have all the resources to do that. And again, I think we're getting there very quickly. Before I wrap up, I want to mention all the people who have been doing that as a team. You saw that before. Thurston and Shan has been supporting us at Norton tremendously. It's been great working with those guys. I know you all are hearing that Norginet and Shan, it's not a good story, and we're at war with Europe. For this kind of stuff, absolutely the Shan team, people agree, wherever they are, they've been great. We love working with those guys, and we're making great advances with them, so I don't know where all this story about conflicts come from. But also, lots of other people have been contributing. University of Amsterdam, some of the software you saw before, the monitoring page has been done by people there. FUNET, Dyke has been doing lots of support for this. All our friends and enemies and in the NSI working group, we're very happy for those. The great thing about that group is they will tell us when we're idiots, and we need that, because otherwise we're going to do dumb things to it. So that's really important. Thank you for that. Esther in particular has been supporting us a lot. The Glyph community, same story, they're supporting us a lot. We've been doing lots of early presentations and early discussion about use cases with the LSI community, they're very important to us. And the Dutch and Internet 2 International Enlighten Your Research Initiative, provoking science groups to go out and try some of our new technologies has been really important to us. We're very happy about that. So, are we done with all this stuff? Well, some of you have seen this slide before. We know how to do the transport for the circuit capability, we know how to do the cross connects. And usually I've been doing this without a SIG for the authentication, but we have that one now. Identity management, more or less. Security, we have a security manager, and he will disagree with me, but I think we're getting there. Topology has changed. Well, I think we haven't. It's a tick, but I hear all these people out there who have another story, so I just have to convince them. Performance verification end-to-end, Jerry, you're fixing that problem, right? Link policy management, not really. Service level management, no, not really. Virtualization of all these resources, not at all. Service architecture as override path exchanges, which is critical for the international deployment of this. Rob and I have promised to have this problem solved by next week, so we have to get some work done. And then security apparently has to be there twice because we have the security management. So there's much to do yet. So I thank you for listening, and I hope somebody will join in and solve the rest of the problem for me.
Thank you, Lars. One or two questions, and then we're done and let you go to the opening reception.
Don't be shy, ask questions. I'm just between you and your drink, so no worries.
Okay, let me try one question, Lars. Norgenet is building a 100 gig network all across the Nordics, towards Hamburg, Amsterdam, London, connecting Hamburg and Amsterdam and London with other networks. 100 gig all the way. Why do we need BOD?
I think we need BOD for a bunch of reasons. I think we need, lots of people are using it for firewall bypass within science communities that want to understand that the circuit goes behind their firewall from their resource to behind the firewall to another resource, and it's theirs and they control it all the way. We have users who want to understand, not necessarily making sure they have 100 gig, but that they have understandable performance characteristics, so they want to know that the circuit goes from here to here with this particular routing with something they control, so it does the same thing every time. There's lots of use cases that need this stuff, so I think there's plenty of reasons we need this. Plus, yes, we have 100 gig across all of Northern Europe, but we don't have 100 gig to Korea or New Zealand, where I'm going next week, or anywhere else, and we have people here this week who are experimenting with sending 4K streaming video between stuff that is going on here and New Zealand, and that is not necessarily going to fly on the best effort network. So we have to realize we're serving people who want more than just best effort, even on our 100 back platform. So I think it's absolutely essential.
Okay, thanks. One more question? No? Then I would like to thank Lars once more. I would like to thank you as an audience for being here and listening carefully to all the interesting speeches from Arne, from Rob, and from Lars. In half an hour, the opening reception will start here in this building, in the Chancellor Room. It's lasting roughly 90 minutes. There's drinks, there's light snacks, there's no dinner there. So after the opening reception, please feel free to go out to dinner on your own and bring your friends and network and share knowledge. That's what we're here for in this old university. Thank you all. Have a nice evening and see you tomorrow.
You were ticking my shoulder with it. Yeah. I probably put it in the pocket of my jacket. Yeah, but I took off this one.